All right, guys and gals. So we have moved out of our first unit of study. We're now into Unit 2, which deals with triangles. So today we're going to keep things very basic, very simple. Chapter 4, sections 1 and 2 will be covered in just this one video. So just a heads up, both sections, one video, all good. So what we're going to start with is just the very basics. We won't get too technical today. And then as we move forward, we'll start getting into more complicated issues. So let's start off. Triangles puts us into a realm that we call polygons. All right, poly meaning many, and then gon referring to the sides or the faces of a figure. So a polygon is simply a closed-sided figure with three or more sides. So a triangle, if we're going to define it, is a polygon with three sides. And how we define things is going to be very, very important. So make certain that we understand what a triangle is. And I know for most of us that seems like a silly thing, but definitions are going to be very, very important from here on out. So make sure you're keeping up with them. Let's talk about some other ideas about a triangle, just some words that you should know. Parts of a triangle. First, obviously, triangles have angles, right? And an angle references not only the vertex, but the sides. The vertex itself is just this point where the sides meet. So obviously, three angles, three vertices for a triangle. The sides, again, are what we go from vertex to vertex. All right, so three sides. And remember, the sum of the measures of the angles of a triangle is 180 degrees. And we call this the triangle sum theorem. Yes, it is a theorem. So this is something that we can prove. One way to prove it is take a triangle, cut it out of paper, cardboard, whatever, and then tear each of the corners off. All right. So if I were to tear each of these corners off, I could reassemble them. So maybe this is, I don't know, 1, 2, 3. So we have 1, 2, 3. We could assemble those corners all together and they would create a nice straight edge. So that's one way we can prove it to ourselves that, hey, all the angles on the interior of a triangle add up to 180. There are other ways of proving this, however. And I've lost my page. Where did it go? Well, we'll get to it in a minute. We'll prove it here in just a second. Everything's out of order. We'll get it figured out. Let's talk about some other issues with angles then. So take a look. If we're talking about the three angles that are on the interior, then obviously we could also talk about angles on the exterior. So let's be specific here. If we're talking about exterior angles, we create those by taking a side. So for example, in this case, side AB, and then we extend that side. Okay. So there would be that exterior angle. We'll call it 4. All right. The other two angles on the inside here, 1 and 3, we refer to these as remote interior angles. Now, here's the neat part about remote interior angles. If I were to add up the measures of angle 1 and 3, they will equal the measure of angle 4. All right, and I can prove that to you pretty quickly. So take a look. This is what I'm claiming. All right, let me prove it to you. So the first thing I can tell you is that the measures of angle 1 plus the measures of angle 2 plus the measures of angle 3 all equal 180 degrees. And I could prove that to you based on our triangle sum theorem, which we'll prove later. I can also prove to you that the measure of angle 2 added to the measure of angle 3 is also 180 degrees. I know that, oh, excuse me, not 3, 4. Helps if I can read. There we go. And I know this is true because take a look. 2 and 4 are a linear pair by definition. If they're a linear pair, then by the supplement theorem, I know that these will add up to 180. And by the definition of supplementary, there we go. So notice both of these equations on the right-hand side add up to 180. So one thing I can do is take the measure of angle 1, add it to the measure of angle 2, added to the measure of angle 3, and set that equal to the measure of angle 2, added on to the measure of angle 4. And what do you know? They both have a measure of angle 2. So I can take those out and then see very quickly that the measure of angle 1 added to the measure of angle 3 must equal the measure of angle 4, which is what I set out to prove. So the two remote interior angles added together will equal this exterior angle. All right, so that's something important. Definitely want to know it. Let's try something else. Let's talk about types of triangle real quick. We can classify triangles different ways. One way is by angle. The other is by the sides. I guess angles would be the correct way of saying it there. So take a look. We can have an acute triangle, a right triangle, and an obtuse triangle. So acute triangles mean that all three angles are acute. Okay. In a right triangle, we would have just one right angle. And then in an obtuse triangle, we would have one obtuse angle. Obviously, we couldn't have more than one obtuse, or you wouldn't have 180 degrees. Same here. We couldn't have more than one right angle. If we had two, that's 180, and we don't have anything left for the third. Let's talk about sides. Equilateral means that all sides are equal, so, something like that. Isosceles, again, something like this, where two sides are equal. And then scalene, which means no sides are equal. So here's what I want you to do. Take a moment on your own and see if you can recreate this grid. And I want you to try and draw every single type of triangle possible. So for example, in this first box, I want you to draw a triangle that's not only acute, but also equilateral. In this box, draw an isosceles triangle that's also acute, and so on. How many different types of triangle exist? So pause the video for a moment, see what you can draw, and we'll come back in a second and see what you found. All right, well, let's take some drawings here. And again, when I say drawing, we're really not drawing. These are more rough sketches. But take a look. I know I can draw an equilateral acute triangle. It would look something like this. All sides are the same. All angles are acute. And we're good to go. I could also draw an acute isosceles triangle. Very simply, we could draw something, say, like this, where we've got two sides here that are the same. This side is different. All angles are acute. Scalene acute triangles are a little bit tricky to draw, but let's try to do one as best we can. That's pretty good. So 1, 2, 3 different side lengths, 3 different angles. I know those look close, but trust me, you can do it. Let's talk about some others. What about an equilateral right triangle? Well, notice with an equilateral acute, in order for all the sides to be the same, all the angles have to be the same. So there is no way for me to have this one drawn. So this is one that simply does not work. What about a right isosceles triangle? Well, that's very doable. Let's draw 2 sides that are the same, and then this third side that's going to be just a touch longer. So it would look something like this. What about a right scalene triangle? Also very doable. We could draw something, say, like this. So there's our right triangle, and then there are our 3 different sides. So very doable. Equilateral obtuse. Well, equilateral obtuse doesn't work for the same reason that a right equilateral does not work. We've got to have all 3 of those angles end up being the same size. So no joy. What about an obtuse isosceles triangle? All right, well, these are very doable. We'll draw 2 sides that are the same length and then connect the dots. So these 2 sides are the same, with this side being just a touch longer. And then last but not least, a scalene obtuse. Again, very possible. We'll just draw one of those sides a little bit shorter. So we've got one side, a second side, and then a third side, all of varying lengths. So at the end of the day, there are only 7 different triangle types. All right, so just 7. Just 7. Onward and upward. Let's try some things. So take a look. In this example, we know that our triangle is equilateral. And we're trying to find the measure of each side as well as the value for x in this case. So notice RS, that's this side here, is x added to 9. ST is this side here, and it's equal to 2x. And RT is 3x subtract 9. And we're trying to figure out, again, how long is each side, as well as what is the value for x. So let's do that. So since any of these sides are going to be equal to each other, I'm going to grab, say, these 2 and say that 2x is equal to x added to 9. And in this way, I can solve for x and figure out what my side lengths are at the same time. So I'm just going to subtract an x here. We'll subtract an x here. X is simply 9. All right, well, let's plug it back in, and we'll see what each side is and make sure we're all good. So if I plug a 9 in here, 9 added to 9 is 18, so that looks good. 2 times 9, also 18. 3 times 9 is 27. 27 less 9 is also 18. So cool, we've done it correctly. We know the side lengths. We know what x is. We've solved the problem. All right, let's try another one. And I apologize here. Some things kind of got weird. First off, this is x degrees. Every time I open the file, that x gets smaller and smaller. One of these days, it is just going to disappear. And we're asked to find the value of x in this triangle. And by the way, the symbol for triangle, which kind of bled into the A there, is simply a triangle. So if I wanted to talk about triangle ABC, then this is how we would do it. If I wanted to talk about triangle CBA, then we could write it that way. And notice in this case, these two triangles talk about the exact same figure. So again, we know by the triangle sum theorem that if I take 55, 58, and x and add those together, we know that they should equal 180 degrees. So if I go ahead and add this up, we get, what is that, 113 added to x, we don't know, is 180 degrees. We'll go ahead and subtract that, 113, 113. And we get that x is equal to, what is that, 67? 67 degrees. So these are going to be the kinds of problems that we'll be working on. Nothing major, just got to know some things. However, let's get into the proof. All right, because yes, proof is going to come back. It's going to haunt us all year long, so we might as well enjoy it. Here we go. The triangle sum theorem, as we talked about earlier, and again, I don't know why these files or these things are out of order, but we'll deal with it. The triangle sum theorem states as follows. The sum of the measures of the angles of a triangle is 180 degrees. The question, of course, now is why? So one way I showed you is to simply take a piece of paper, cut out a triangle, tear them up, and then you could simply put the angles together, and you'll see that you'll get something, as we said earlier, that might look like that, where 1, 2, 3 angles, and you get this nice straight edge for a full 180. Here's a more formal way of proving it. So here we go. The first thing we're given is that we've got a triangle. So notice they drew just sort of a nice nondescript triangle here. Excuse me. So that part was simple. We're going to try to prove that the measures of the angles in here, so instead of playing alphabet soup, we've numbered them. So that the measure of angle 1, 2, 3 add up to, again, that full 180. So let's get started with the proof. And I've gone ahead and left all the statements out. It's up to us now to figure out the reasons. So that first one, there's really not much to say. Triangle ABC is what we were given. So that part's easy. Now, this next part's tricky. And I say tricky, not really tricky, it's more clever than anything. We're going to draw a line AD through A that is parallel to BC. So what allows me to draw this parallel line? Well, one thing we could say is that, hey, you know, between 2 points, there's exactly one line. Another thing that we can say is through point A, not on BC, there is exactly one line parallel. And that's what we're going to say, that there is one line through A parallel to BC. And not just the fact that there's one line, but there's exactly one line. Let's be specific. Now that we've got that figured out, so we know that BC and AD are parallel based on what we've got here. Notice now it's going to tell us that angle 4, so this angle here, and angle BAD, so BAD, all of this in here, is a linear pair, and I know that simply by definition. So this is definition of a linear pair. They meet all the requirements. They're on a straight line together. These two angles are adjacent on that. They share a common vertex. Cool. They're a linear pair by definition. All right, let's look at the next one. It says that angles 4 and angles BAD are supplementary. And we know that because of the famous supplement. Well, there we go. Supplement theorem, which states, hey, if we've got a linear pair, then wonderful. They're supplementary. And then we can take this one final step. I know that the measure of angle 4 and the measure of angle BAD added together equal 180. We know this by the definition of what it means to be supplementary. Cool. So we've gotten to this point. We know that angle 4 and angle BAD added together now equal 180. Excellent. Let's keep working. Notice that the measure of angle BAD is equal to the measures of angle 2 and angle 5. So notice we've got this larger angle, and angle 2 and angle 5 are the smaller angles within. So I know that works by the angle addition postulate. Very good. Next, I'm going to take step 5, and notice what we've done to it. We've kept the angle 4, we've kept the 180, but we're going to take BAD out, and we're going to put angles 2 and 5 in its place. So this is simply a substitution step. Very good. Now, let's look at something. Angle 4 is congruent to angle 1. Okay. And here it tells me that angle 5 is congruent to angle 3. Well, what allows me to make that statement? Well, let's look at just 4 and 1 for a moment. They're interior between the two lines. 4 is on the left at the top, 1's on right at the bottom. Those are alternate interior angles. Because we've got parallel lines and we've got alternate interior angles, then we know that they are congruent based on the alternate interior angles theorem. So let's write that down. So the alternate interior angles theorem. Excellent. Now notice we're going to take it from there that not only are these congruent, but we can also say now that they are equal. This is by definition of congruence. And then last but not least, so take a look. Let's go back up here to 7, because that's going to play a key role in how we get to 10. Notice in 7, we said that angles 4, 2, and 5 add up to 180. So again, 4, 2, and 5 add up to 180. But we just figured out that 4 and 1 are the same, and that 5 and 3 are the same. So that means I can substitute angle 4 for angle 1. I can also substitute angle 5 for angle 3. So this is simply a substitution step. And I can see very clearly now that angles 1, 2, and 3 all added together equal 180. So if you need to take a moment and look at that and reread it, by all means, but this is how we'll prove our triangle sum theorem. This is how we know that every triangle contains 180 degrees. All right, let's take a look. The exterior angle theorem. We talked about this earlier, so let's number these real quick. Maybe we got angle 2 and 3 in here. And we gave kind of a rough proof earlier, so we won't repeat it. But again, if I take angles 2 and 3 and add those together, so the measure of angle 2 added to the measure of angle 3, we'll end up with the measure of angle 1 on the outside. And again, we gave a very quick proof of that earlier. Both of these ideas, not only the exterior angle theorem, but the triangle sum theorem, are big, big ideas in this unit. So make certain that you know them, what they say versus maybe what they don't say. All right, don't try to reach for this if it's not what you need. Last but not least, we've got some other ideas. Let's talk about this. We have yet to use this word. Let's talk about what a corollary is. A corollary is a real fancy word for a theorem. Okay, and in this case, a theorem, that M turned out terrible, a theorem that follows from another. So, for example, these are the triangle sum corollaries. There are 2 of them that our textbook gives us. Okay, a corollary is simply a theorem that directly relates to another. So if I know one, then by default, it kind of leads me to another. That's what a corollary is. So take a look. In this corollary, we're told the acute angles of a right triangle are complementary. So let's think about that. Here's a right triangle, ABC. I know that angle C is the right angle. Well, because of the triangle sum theorem, I know that the measure of angle A added to the measure of angle B added to the measure of angle C all has to be 180 degrees. But remember, we said this was a right triangle, then angle C is 90 degrees. So the measure of angle A added to the measure of angle B added to 90 is 180, and that was a quick substitution step. Notice I could subtract 90 degrees from both sides using our substitution property and a little bit of, subtraction property. And then with a little bit of substitution, I can very quickly see that the measure of angle A added to the measure of angle B has to be 90. And by definition, that makes them complementary. Cool. This next corollary is a little bit trickier. There can be at most one right or one obtuse angle in a triangle. And again, we could go back very quickly to show that, for example, let's say that the measure of, I don't know, let's say L is our right or obtuse angle. Okay, we could say that this, the measure of angle L, has to be greater than or equal to 90, right? And then we could follow from what we did here. Well, if it's greater than or equal to 90 and use that constraint up here, we could see very quickly that it's the only one that would meet that constraint. So again, proving this could be done algebraically. But again, corollaries are simply ideas that follow from another. In this case, both of these corollaries follow from the triangle sum theorem. All right. One last thing to discuss, and this thing's pretty simple. Ratios. A lot of times SAT, ACT, they'll use problems like this to try to mess with your head, and they're really simple. So let's do one real quick. It says the measure of the angles of a certain triangle are of the ratio 1 to 4 to 7. So for example, if I were to draw just sort of a nondescript triangle here, who cares what it looks like? If I were to look at their angles, this angle, for example, would be 1x, one part. This one would be 4x, or 4 parts. And that this angle would be 7x, or 7 parts of the total. Again, 1 part to 4 parts to 7 parts. What are the measures of the angles? Well, notice, because we separated them up into parts, one part, this one has 4 of the same parts, this has 7 of the same parts, we can use x to represent however large that piece would be. And we know that all 3 of these added together, well, if my pen would write. So if we have 1x added to 4x added to 7x, we know that has to be 180 degrees. Well, we can go ahead and combine those together. That's 12x equals 180 degrees. We could then take that and divide. So I know x is, let's see here, I know 12 goes into 18 once with 6 left over, and 12 goes into 65 times. So x represents 15 degrees. So then we could take that 15 and start plugging it in. So this angle is 15 degrees. 15 times 4, what is that? 60 degrees. So if we added those two together, that gives us a grand total of 75. So that means this has to be 105 degrees, or 7 times 15. So again, if you see problems like that, that's how they work. They're not that big a challenge. So when I see you in class next, all of these ideas that we've discussed about just triangle basics are going to be fair play. If you've got any questions, make sure you write them down in your notes. That way, when you come back to class and I say, do you have any questions, you know what to ask. Have a good day, guys.